Okay, so we're actually starting an entirely new topic today of approximation algorithms. So until now, the entire course has been devoted to finding fast algorithms for solving problems. And of course, what that means is getting the right answer, getting the optimum, the max flow, the shortest path, and so forth. For the next week or so, we're going to be talking about problems where we know a priori that it's just not feasible to find the optimum answer. Within computer science, we have a very nice formalization of this, right? Until now, we've been looking at tractable problems. And the real question has been, how fast? But now we're going to look at intractable problems. Where it doesn't make sense to ask how fast we can get to the optimum solution because we can't get there at all. So instead, we're going to be asking how good a solution we can get if we can't get to the very optimal solution. Within computer science, we've really formalized the notion of complexity of a computational problem. And we have this whole large class of NP-complete problems, which are believed intractable to solve efficiently. Okay, and I'm assuming that most of you have encountered NP-completeness before. Now, we don't know that they're intractable. There might be some huge breakthrough algorithm. I mean, again, there is a final project in this class, and anybody's welcome to prove P equals NP. But I'm actually going to take it as a given so that I don't have to keep repeating myself, that P is not equal to NP, that NP-complete problems are just not things that we can solve in polynomial time. And so we're going to need to look for other, for alternatives. Now, actually, in practice, sometimes there are problems that are polynomial time, but are still, the best known algorithms for them are too slow to be used. And so even for some tractable problems, we're sometimes going to need to look for alternatives. So what are alternatives to exact solutions or to complete solutions? Right, so one is special cases. Okay, so maybe I can't find the a graph coloring in any graph, but if I only need to find graph colorings in perfect graphs, then it turns out that this is a special subclass of graphs for which there is an exact solution, or graphs of low tree width, or graphs of small depth. There are various sort of special cases of problems where it might be possible to get an algorithm that works well. Another thing that people have often studied is random inputs. We talked about this a little bit when we were just talking about linear programming, that we don't know if simplex can be implemented efficiently in general, but it has been shown that if the input is a kind of randomly perturbed instance of a linear programming problem, then there is a polynomial time algorithm. Of course, in practice, things aren't random. You always get the worst case from your advisor. So that also has limitations. Another option is to explore slightly non-polynomial bounds. So we always worship polynomiality as the ideal for a runtime. But sometimes you can get close to polynomial even if you can't get all the way there, and in practice that might be good enough. So there's some work on, for example, just improving the exponent of an exponential time algorithm, right? So if you're able to improve something from 2 to the n to say 3/2 to the n, you've just made it a lot faster, and you may now be able to solve problems that are large enough. Another option is heuristics, where you just run an algorithm that has no guaranteed performance, but that is fast in practice. And you hope for the best. You just hope that whatever input you give it is in fact going to be fast. But we are going to look instead at a particular class of approximation algorithms. And to define an approximation algorithm, well, we start with an optimization problem. And an optimization problem is defined by a set of instances and solutions to an instance. So this is a set of solutions and some sort of value function which takes each solution to a real number. And a maximization or minimization goal. And once you've defined all of this, the optimization problem wants to find the best solution, which we denote by opt of that particular instance. So for example, actually, do I want to do it? No, let's go on for a minute first. So now let's do an example. So one of the problems that we'll be looking at is called bin packing. So the idea here is that you've got a bunch of items of different sizes. And you want to distribute them into a collection of bins of size 1. And your goal is to minimize the number of bins. Okay, so this is about, fitting everything in your suitcases when you're going to college. And so, an instance here is defined simply by a collection of items. A solution is a collection of bins and an assignment of items to those bins. That's interesting. The value is just the number of bins in that solution. And of course, our goal here is a minimization goal to use the smallest possible number of bins. Okay. Now there are some technical assumptions. We often assume that the inputs and the range of the objective function are integers or maybe rationals, since we don't know how to deal with real numbers. And this way we can do things like linear programming or binary search. We also tend to assume that the objective function applied to a particular solution is a polynomial size number, right? We don't want to be prevented from solving the problem just because we can't write down the value of a particular solution that we're looking at. Okay, and in general, we look for an algorithm which is going to be polynomial time in the bit complexity or the bit sizes of these numbers. Okay. Now, when we're talking about NP hardness, NP hardness actually talks about decision problems, right? Technically, the definition of NP hardness is about it's being NP hard to decide whether the answer is yes or no to a particular question. But you can always take an optimization problem and turn it into a decision problem, where you decide if the optimum is greater than or equal to some value k. Okay, and we say that an optimization problem is NP complete or NP hard if the corresponding decision problem is. Right? And obviously, if you could actually solve the optimization problem, then you could also solve the decision problem. So this is just a typical way of reducing from this optimization, from decision to optimization. So now I can finally define an approximation algorithm. So an approximation algorithm is one that for any input, it gives a feasible output. Right, so for any input, which we were denoting by I, it gives some feasible solution from the set of solutions S of I. So that's the whole definition of an approximation algorithm, is that it gives a feasible solution. So can somebody give me an approximation algorithm for the bin packing problem?
We pack ingredient like how I
Oh, that's much too sophisticated. Give me something simpler.
Throw it in a bin. If it doesn't fit, make a new bin and throw it in that one.
That's greedy again. That's still too complicated. Give me something easier.
Just pack one item in each bin or something?
Yes, one item per bin.
Oh.
Got to learn to be lazy. So that's an approximation algorithm. Okay. Of course, the question is, how do we measure the quality of an approximation algorithm? Right. And in general, the way we measure the quality of an approximation algorithm is by measuring the quality on a specific instance and then consider the worst case over all the instances. There are other things you can do. You can measure the average. You can measure the average over instances, but we are going to do the usual thing of just asking for a given algorithm, what is the worst instance for it? What is the worst approximation quality that it is able to achieve? But even if we're talking about approximation qualities for specific instances, there's still a question of defining that quality. So the first measure of quality that it might be obvious to think of is what's called an absolute approximation measure. Okay, so we call an algorithm a k-absolute approximation algorithm if for any instance of an input, the value of my algorithm is within an additive factor k of the value of the optimum for that instance. Okay, so we measure the performance on an instance by the difference between the instance and the optimum, and we measure the performance of the algorithm by looking at the worst case over all instances, the biggest difference between the algorithm and the optimum. Does that make sense? So let's give some examples of absolute approximations. And this also gives me a chance to start introducing some of the problems we're going to be looking at approximating. So the graph coloring problem is pretty famous. Okay, so you're given a graph G, and your goal is to assign a color to each vertex. And the requirement is that no two neighbors have the same color. Okay. And the objective is to minimize the number of colors that you use. Okay. So this is a very famous NP hard problem. It's a very hard one. It's actually hard to even approximate well, and we'll come back to that later. But planar graph coloring is a special case, right? If your graph is a planar graph, which is to say that you can draw it without having any edges crossing. Okay. Coloring a planar graph is easier than coloring a general graph because it's a restricted subset of the graphs. And this is equivalent and also known as map coloring, right? So somebody gives you a map of various countries and you have to color each country with a color so that no two touching countries are given the same color. Okay. And this saw a lot of work, a lot of research, a lot of incorrect solutions. But there's a very famous theorem called the four-color theorem, which says that any planar graph is four-colorable. Okay. So what can we do in terms of approximation algorithms? Well, I should say that it takes some work, but you can actually, this is actually algorithmic. Okay, so you can actually take the proofs of four colorability and turn them into an algorithm for four coloring a graph. Okay, so that immediately gives us a four approximation algorithm, right? Actually, I claim it's a three approximation algorithm. Is that right? Why is it a three approximation algorithm if you can four color a graph?
Well, you need at least like one color in general.
Right. You're going to always use at least one, right?
What if there are no vertices in the graph?
Well, so what should you do if there are no vertices in the graph?
Use no colors at all.
Use no colors. So that's actually where I was going to head, right? So can we do better than a three approximation, right? So we know we can always do four colors, but let's think about how far off that is going to be from optimum. So we've just said that if there are no vertices, we use zero colors, but that gives us an exact algorithm with zero colors, right? Now, the idea of a three approximation comes from the idea that maybe you can use one color when you, maybe we're using four colors when you only need one. But what can we say about one colorable graphs?
No edges.
Right. As soon as there's an edge, you know that you're going to need to use a color. You're going to need to use two colors just to handle that edge. So that means that all of the vertices are isolated. Again, it's easy to do an optimal coloring, right? We just use the same color on every vertex. What about two colorable graphs?
They're bipartite.
Exactly. Two colorable is just another name for bipartite, right? So what can we do about that? Do we need to use four colors if we have a two colorable graph?
No, you can just use the like any two colors, right?
How do we know how to use them?
You can check if there's no cycle or a cycle of odd length.
Okay, so no odd cycles. That is another characterization of bipartite, but it's kind of a negative characterization. How can we actually color the graph?
Well, you
Start
color
by
a given
coloring-
vertex. Oh, yeah.
Sorry, go ahead.
Start by coloring one vertex and then just for all its neighbors color the other color. And if you see
Yeah.
a contradiction.
Basically, greedy works here. You color a vertex, and then you invert for the neighbors to the other color. And then you go back for their neighbors, and so forth. And the lack of odd cycles means you'll never get stuck, right? This coloring will just work. And so therefore we can be exact on 2 colorable graphs as well. So in fact, it's only when we get to 3 colorable graphs, right? For 3 colorable graphs, it turns out it's actually NP hard to tell whether you are 3 colorable or a 4 colorable planar graph. So at that point, we just use 4 colors. And that's the only time when we might be suboptimal. So in fact, this is a 1 approximation, or a 1 absolute approximation.
I have 2 questions.
Yes.
Yeah, so first of all, when we're talking about 3 approximation, is it still supposed to be 4 approximation if we just apply the algorithm directly, because we don't make like any special case with 0 colors?
Exactly. If we just say use 4 colors without thinking at all about the problem, then all we can say is that that's a 4 approximation because the number of colors is going to be non-negative.
Yeah, so it's
You
not
gotta
a
take
big
that
approximation.
little extra step in order to differentiate the 0 color case.
Yeah. And second question is, can we just say that every graph can be colored in 3.5 ways to get a 0.5 approximation?
So that has to do with whether you want to talk about an algorithm that outputs a number or an algorithm that outputs a solution. Okay, so yes, if we say, if when we're not sure, we give an answer of 3.5, then we're actually within a half of the correct answer in terms of a number. However, if our requirement is that you actually produce a solution and look at the value of that solution, then the best we're going to be able to do is 4. And in that case, we're getting a 1 approximation. And that's what we generally ask for, is that our algorithm should not just give a number, but should actually offer a solution with that number. Okay? And I mean, that's sort of an arbitrary decision, right? But that sort of is the common way of talking about approximation algorithms. Okay. Now, this analysis that we did for graph coloring is the graph coloring problem that I told you about is actually what's known as the vertex coloring problem, because you're assigning colors to the vertices. But you can do another variant of coloring where you talk about edge coloring, where 2 edges have to be different colors if they share an endpoint. And there's a famous theorem due to Ising that every graph of degree delta, well, if the degree of the graph is delta, what can we say about the number of colors needed to edge color that graph?
At least delta.
Yeah. So it turns out that the only other possibility Sorry, folks, my computer just rebooted, and I've activated audio on my pad. Can people hear me?
Yes.
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 All right, I'm going to continue then. So Ising's theorem says that every graph of degree delta can be colored with delta or delta plus 1 colors, and is algorithmic. And so that also is a 1 approximation algorithm. Okay, people hearing me okay while I'm out, while I don't have the Zoom app in the front?
Yes.
Okay, good. All right, so additive approximations are nice when you can get them, but it turns out that additive approximations are often impossible. Hang on a sec, let me see if I can reduce that noise. Unfortunately, there's some construction going on outside, but I think it's for one day only. So additive approximations are often impossible. And to demonstrate that, I'm going to introduce you to another famous NP-hard problem, which is called the knapsack problem. So the idea here is, actually, I sometimes like to call it the shoplifting problem. So, you know, the idea is if you sort of are going to sort of sneak into a store and try to shoplift as much as possible, there's only a limited amount of space in your pockets for taking stuff out with you. And so you'd like to make as much profit as possible from doing this. So we can model the store as a collection of items with profits piece of I, and our pocket as a sack of size B. And besides these profits, the items also have sizes, SI. And our goal is to find a maximum profit set of items of total size less than or equal to the knapsack. Okay, and I am going to assume, without loss of generality, that all of the profits and sizes are integers, and B are integers. Because if they're rationals, I'll just multiply everything out in the beginning, and I'll still have polynomial size numbers to work with in terms of the number of bits. Okay? So this is an NP-hard problem. We're not going to be able to solve it exactly. But now, suppose that I have some K absolute approximation for it. I'm going to prove to you that it's possible to turn it into an exact algorithm, which is going to polynomial time algorithm, which is going to contradict the NP hardness assumption, or again, is going to imply that P equals NP. Okay? So people understand where I'm headed? And people still hear me?
Yes.
Yes, okay, good. So how am I going to do this? Well, I'm simply going to multiply all of the PI by K plus 1. And then I am going to find my K absolute approximation to the optimum. And I claim that this is going to actually give me the optimum solution. Can anybody tell me why?
I mean, the solution can only be increments of your individual costs of your objects. So if the increments are bigger than K plus 1, well, yeah, that sort of implies that whatever your approximation is, right? If it's going to be as close as K, then it has to be like 0.
Exactly. It's a rounding argument. right? So the point is that if I multiply all of the prices by pi, this also multiplies by k plus 1. This also multiplies the optimum by k plus 1, right? But the optimum was originally an integer. So now the optimum is a k plus 1 multiple, right? So my approximation algorithm finds and in fact, every solution is a k plus 1 multiple. And so that means my approximation finds a k plus 1 multiple that is within k of opt, right? So it found opt. Does that make sense? So this is this is a killer of additive approximation algorithms, because in almost every problem that we've on to multiply the costs in a sort of uniform way that also multiplies the objective function in the same way, right? Certainly any sort of problem with a linear objective function is susceptible to this kind of transformation, and therefore is not going to have an additive approximation, okay? In fact, sometimes this can even be applied when you don't have numbers. So another interesting problem that we can look at, what's known as the independent set or clique problem, or max independent. Which is also known as the max, or equivalent to the max clique problem. So here you're given a graph G, and you want to find a maximum subset of the vertices with no, or for a clique with all connecting edges. Okay. So this again is one of the famous optimization problems in computer science. It was one of the first problems to be shown NP complete. So we're not getting an exact solution, okay? But suppose that we have a K approximation, a K absolute approximation. So we can always find an independent set that is that has at least as many that has within K of the maximum possible number of vertices for an independent set. Now, on the surface, it doesn't look like I can apply my multiplication trick here because there are no numbers, but I claim that I can nevertheless multiply the problem in a way that makes the optimum solution, that makes the absolute approximation into an exact solution. Does anybody see how to do that?
Would you duplicate the graph or?
Exactly. So what I can do is make K plus 1 copies of the graph. What does this do to the optimum solution?
Multiplied by k plus 1.
Well, that does that. So yes, right. So the point is that the new optimum is K plus 1 independent copies of the old optimum. Actually, I don't even need to know that that's the new optimum. It's enough to know that it is a feasible solution. Okay. So some of you may question whether this is optimum, but you'll all agree that this is feasible, right? Because these vertices were independent and the copies are independent of each other, right? So I find this bigger independent set. What does that give me? And so now suppose that I find my K absolute approximation, okay, which is going to have whatever K plus 1 times opt vertices, right? Sorry, minus K because of the approximation factor. Now what do I do? How can right, my job is to find an independent set of the original graph.
By pigeonhole, you have at least one graph where you have like more independent vertices.
Right. Pigeonhole is what we're doing. Is what we're going to do here, right? So basically, what I can say is that there's an average of K plus 1 opt minus K divided by. Okay, let's see if I can get my. I have a better microphone on my laptop, so I prefer to use that. Let me disable. Can people hear me? Oh, shoot. Fix that. Okay. Audio good?
Yeah.
Okay. So we have an average of the total number of vertices in the independent set divided by K plus 1, since there are K plus 1 copies, vertices per graph. So some graph has at least this many.
Professor Carter, are you
Yes.
sharing your screen?
I am sharing my screen. Are you not seeing it?
No.
All righty, let's try that again. Better?
Yes.
All right. So some graph has more than, has at least the average number of vertices, which is going to be just opt minus K over K plus 1 vertices, right? But what can I say about this if the graph has more than opt minus K over K plus 1? Well, this is more than opt minus 1, right? And that means that it actually has opt, since the solution here is an integer. Right, so once again, having a absolute approximation algorithm for this independent set problem would immediately give me an exact algorithm for the independent set problem. Okay, so absolute approximations are very rare. And for that reason, we turn to a more robust notion of approximation known as relative approximation. So again, we talk about worst case over instances. So we say that a alpha an alpha approximate or an alpha times or an alpha optimum solution for an instance I has value between opt of I divided by alpha and opt of I times alpha. Okay, or more precisely, it is at most alpha opt of I for a minimization problem and at least opt of I over alpha for a maximization problem. So you'll notice that the way that I've defined this, alpha is at least 1 to be interesting or to be possible, right? And an algorithm is called an alpha approximation algorithm is one that always outputs an alpha approximation. Okay. And we also say that its approximation ratio is alpha. Now, just to make things a little bit complicated, some scientists actually invert this and use an alpha that's smaller than 1. Right. So for an alpha less than 1, then we say that its value is less than the optimum divided by alpha for a maximization problem and bigger than alpha times the optimization for a minimization problem. Okay. But this is always clear from context. Because if you're using this alternative characterization, then you know that alpha is going to have to be, it's going to have to be less than 1, right? So if somebody tells you that they have a 4/3 approximation, then you know that they're using the first definition. If they tell you it's a 3/4 approximation, you know that they're using the second definition. Is that clear? Okay, so this turns out to be a much more robust notion of approximation. Many NP-hard optimization problems have relative approximations. And we're going to be spending the next lectures just proving, sort of studying how to design such approximation algorithms and how to prove their performance. Okay. So there is this general question of how do you prove an approximation ratio if you've got a particular algorithm. The problem is, what do you compare it to, right? You cannot compare the output of your algorithm to the optimum because you can't compute the optimum. So how do you know whether you're getting close to the optimum? Well, the trick is always to compare to appropriate lower or upper bounds on the optimum. Okay, and a lot of the cleverness in designing and analyzing approximation algorithms is coming up with the appropriate lower or upper bounds. And we're going to get a lot of practice with that over the next few lectures. Okay, so in a sense, this was all introduction. I mean, we got some definitions out of the way, but we're not going to be working with absolute approximations. We're going to be spending the next week on relative approximations. So we're going to see a whole slew of techniques, more and more sophisticated, for developing approximation algorithms. We're going to start with the easiest and most obvious, which is greedy algorithms. Okay, so many algorithms can be solved one step at a time. And the greedy algorithm just does the best possible thing at each step. And for some problems, like shortest paths, you can prove that this kind of greedy step leads you to the optimum algorithm. For our NP hard problems, that's not going to be the case. Doing the best thing, keeping your perspective short this way, is going to sometimes lead you away from the optimum algorithm, but we're going to prove that it takes you close in some sense. So let's start by considering the max cut problem. So we've done min cuts for a while. Let's turn it around. We're given a graph G, and we want to find the cut with the most crossing edges. Okay. So how might we tackle that problem? Well, let's be greedy. Let's imagine that we're going to make that cut one vertex at a time. So we're going to go through the graph. We're going to look at each vertex and we're going to put it on one side of the cut or the other. What would be a greedy procedure?
When you look at a vertex, just stick it on the side that currently would add more edges.
Exactly, right? So if you think about it, what that means is we want to place each vertex on the side which is opposite the most previously placed neighbors. Right? We ignore what came before, but we ignore what comes after, and we just base our placement of each vertex on whatever came before. Okay. So how can we bound the performance of this algorithm, right? This is a maximization algorithm. So we're not going to be able to cut all of the edges, but the question is, can we cut some fraction of the optimum, right? So again, we can't say what the optimum is, but can we give some sort of bound on the optimum? What's the most obvious bound of all, possible on the number of edges we can cut?
M.
Yeah. So now we've at least got a target. Okay. Now let's think about our greedy algorithm. What can we say about what it's doing? Well, the way I like to think about this is that when I place an edge, or sorry, when I place a vertex, some of my edges get decided, right? All of the edges that connect me to a previously placed vertex are going to be cut or not cut at this moment. And that's not going to change later, right? This is the decision point for those edges. And it's not the decision point for any other edge, okay? So what can I say about these edges that are getting decided at this moment?
At least half of the decided edges go into your cut.
Exactly. Okay, so at least half of the edges enter the cut. And so if you want to sort of do the accounting, you can charge the uncut edges to the cut edges. And you can conclude that overall, you cut m over 2 edges, at least. And that means that, sorry, in our greater than 1 language, we have a 2 approximation. Is that clear? So very straightforward analysis, but it has all the steps, right? We need some kind of bound on the optimum since we can't actually talk about what the optimum is exactly. And in this case, we used a very obvious, very simple bound. And then we do an analysis that compares the performance of our algorithm to that bound since we cannot compare it to the actual optimum. Okay? Let's look at another problem, set cover. For some reason, my pen loves changing to an eraser, but does not like changing back to a pencil. So set cover. In set cover, we are given a set of n items and a collection of m subsets of them. And we want to find a collection of these subsets that cover the items. Okay. In other words, the union is equal to the whole set or all items. Is the statement of the problem clear? Yeah, okay. So what would be a natural greedy algorithm? How should we start? What's the greediest thing to do at the start?
Add the subset that will add the most items.
Right, take the largest subset. Or take the subset with the most items. Okay, what about the next step? Should I again take the next subset with the next most items?
Not necessarily if there's like a huge overlap.
Right, so what should I be paying attention to?
How many items you're adding with each subset?
Yeah, I'm going to take the subset with the most uncovered items. Yes? So this is the obvious greedy algorithm, right? Just take the most uncovered items possible at each step. Okay. Now the analysis is a little bit surprising, not obvious. Let's suppose that the optimum is equal to k. So I'm now, again, I don't know what the shape of the optimum solution is, but I'm going to use the value of the optimum solution to assess how my algorithm is doing. So if the size of the optimum solution is k, that is, there are k sets that can cover everything, what can I conclude about my first step?
Has to cover at least n over k elements.
How come? First set has to cover at least n over k items. How come?
Pigeonhole.
Go ahead.
Yeah, this is again the pigeonhole, same as we did with independent set, right? If each of your sets covers less than this, then k of them together cannot cover n items. Okay, so if you think about it, what that means is that after the first set is taken, at most 1 minus 1 over k times n items remain. Right? Okay, how about the next step? What can I say about the next step?
We cover 1 over k of the remaining items because the
Exactly.
optimal still covers.
Exactly. It's the same argument. So if you think about it, 2 things can happen when I take the first set. It might be the optimum. I might take a set that's in the optimum, or I might not. Either way, the remaining items are covered by at least k of the, by most k of the remaining sets. Either the whole optimum is still there, or just k minus 1 sets of the optimum cover everything that remains. Okay, so either way, k sets cover what remains. And that means that after 2 sets, we're down to 1 minus 1 over k squared. Of the items remaining, right? And more generally, after t steps, one minus 1 over k to the t times n items remain, right? So how do I finish the argument? Well, sorry, go ahead.
You want to find like the smallest t such that 1 minus 1 over k to the t times n is at most 1.
Exactly, right? So if 1 minus 1 over k to the tn is less than 1, what does that tell me? Well, the number of uncovered items is an integer less than 1. So it must be 0, right? And so we have a cover. Okay. So if I want to solve for this, right, 1 minus 1 over k to the t times n is less than 1. I'm going to use the approximation e to the minus t over kn is less than 1, right? And actually, let me not do it with the approximation. Let me do it a little bit more carefully. So I want a 1 minus 1 over k to the t to be less than 1 over n, right? Which means that I want t times the log of 1 minus 1 over k to be less than minus the log of n, right? Which means that I want t to be bigger than log n divided by minus the log of 1 minus 1 over k. And if you remember from your Taylor series and such, this is approximately 1 over k. So as soon as t is bigger than k times the natural log of n, I have an optimum. I have a cover, okay? So what does that tell me? That tells me that I have a order log n approximation. Okay, and so you'll notice that this is not a constant factor approximation. It depends on the number of items that you start with, but we have given a relative bound on how many sets we use compared to the optimum solution, right? And again, we don't know anything about the shape of the optimum solution, but we were able to compare our algorithm to the value of the optimum solution by actually plugging that optimum value into our analysis. Make sense? Okay, onward. Next problem. Vertex cover. So it's a lot like set cover, but now you're given a graph G and you want to cover the edges with vertices. Okay, that is, I want to pick a collection of vertices such that each edge has at least one of them. Okay. Now I can actually relate this to two of the problems we talked about before, right? So how does this relate to the set cover problem?
You can think of every vertex as a set of edges.
Exactly, right? So this is a set cover where each vertex is a set of its incident edges. Okay, and so this already tells us that there's an order log n approximation. Okay. Now it's actually also related to another problem that I talked about, which is the independent set problem. Okay, so if every edge contains one of these vertices at least, what can I say about the complementary set of vertices? What it tells me is that each edge has at most one of the complementary set. So that means that the complementary set of vertices is an independent set. And vice versa. So you can split up the vertices of the graph into a vertex cover and an independent set. They go together. Okay. And we have this log n approximation, right? And if you think about it, if we try and take the set cover algorithm, all that that's doing is saying, keep choosing the highest degree vertex, because it's going to cover the most edges. Right? But it turns out that in vertex cover, you can do a lot better than this order log n approximation. Okay. And that has to, and we do so by looking more carefully at the optimum. Okay. So if I am given an edge, VW, what do I know about the optimum?
At least one of the vertices is chosen.
Right. V or W is in the optimum. Okay. And I know that I'm going to have to, and I'm going to have to take V or W into my solution, right? The problem is I might guess wrong about which one I should take. But how can I avoid guessing wrong?
Take both.
Yeah, let's just take both. Okay. So this is being not just greedy, but extra greedy. Okay. Now I claim that this actually gives me a very good approximation ratio. Okay. So each time I look at an edge, I can say, opt needs one of these. I'm going to take both. Okay. Of course, once I've done that, I got the optimum. So I can charge my two vertices versus the optimum's one, right? By taking both of them, I have actually reduced the size of the optimum by one, because the rest of the optimum can cover everything else in the graph. Okay. And so I can conclude that I actually get a two approximation, right? Each time I take two vertices, opt gets one. So this simple trick of being slightly more greedy takes me from a log n approximation to a two approximation in vertex cover. Okay. Now, this also points to an interesting fact. I mentioned that the complement of vertex cover is independent set. you'll actually see on your homework this week that there is no relative approximation for independent set. You can't actually get anywhere close to approximating an independent set. So we have here a situation where the complementary problem has no good approximation. Even though the original problem has a pretty good one. And it's worth thinking about why this is. Okay, so let's think about some optimization problem where the set of possible values for the solution ranges between 0 and 1. Okay, so if I tell you to find an approximation to the maximum, okay, if I tell you, hold on a second. Yeah, suppose that the optimum value of my problem is somewhere very close to 1. Okay. So if the optimum of my problem is close to 1, then any solution, then finding a solution of value 1 is a great approximation. Okay. If this were some sort of minimization problem, right? If the actual optimum is 1 minus epsilon, then when I try to, then when I just take a solution of value 1, I get a great approximation. But what if I consider the complement? Okay, if I complement the problem, then I end up with a solution that's very close to 0. And the problem is that 0 is a terrible approximation, right? Its ratio is infinite. Okay, so the problem is that when you take a complement, you can go from a problem that's very, very close to full to a problem that's very, very close to empty. And those problems that are very close to empty tend to be much harder to approximate. Okay. All right. We're slowly moving into more and more sophisticated greedy algorithms. Any questions based on where we are so far? Okay. Let me introduce you to one more. So this is a problem that draws from the domain known as scheduling theory. And scheduling theory is interesting. From our perspective within computer science, it's just, you know, a little sub area of approximation algorithms, which is a little sub area of algorithms. But in fact, scheduling theory is such a large field that there are entire books and entire courses written just about scheduling theory. And there's a tremendous amount of work on how to optimize scheduling theory problems. The general framework for scheduling theory is that you have a collection of jobs. And we always use n for the number of jobs. And we need to run these jobs on m different machines. And we generally want to optimize something. It could be the total runtime to finish all the work. It could be the average completion time of all the different jobs. It can be the waiting time for jobs to get started. And then there may be a variety of constraints. Actually, let me back up to the definition of the machines. Many scheduling theory problems talk about one machine. Okay. Alternatively, we may want to talk about a whole bunch of identical machines. Or we might want to talk about a bunch of related machines that some are just faster than others. Or we might even want to talk about unrelated machines, where some of the machines, you know, I may have a lathe and a saw, and so I can do some of my work with the lathe and some of my work with the saw, and I can't swap one for the other in any sensible way. Okay. These jobs generally have processing times. Should denote by PI. Okay. And then I might have constraints. So I might have preemption of these jobs. It might be allowed or not. Some of these jobs might come with release times for a job J, where you can't start before. You might get deadlines where you're not allowed to finish after. Okay. And so you can see that with this sort of combination of different kinds of machines, different kinds of optimization objectives, and different kinds of constraints, there can be a real combinatorial explosion in just the number of possible scheduling theory, number of possible scheduling jobs. Okay. So we're going to look at a particularly simple scheduling job, which is the problem which is denoted by P and then C max. The P here denotes parallel identical machines. And the C max means you want to minimize the last completion time of jobs on these machines. The two bars in the middle represent that there are no extra constraints on this problem. Okay. So essentially what we want to do is, basically take these jobs that we have and assign them to different machines, right? And if you think about it, the completion time of the last job is just going to be the maximum of the sum on a machine of all the processing times, right? The total processing time on a machine is the time that last job finishes, okay? And all the work is done when the last machine finishes. So what is a greedy algorithm for this problem? Well, let's consider assigning one job at a time, right? That's sort of the natural thing to do in greedy. If you're going to assign one job at a time, what machine should you assign it to?
The one
machine
with
that's
the
going to
least
finish
work.
earliest.
Sorry?
The one with the least amount of work currently scheduled for it.
Yes. So we're just going to assign it to the least loaded machine. Okay. Can't get more obvious than that, right? We just put the jobs one at a time in the place where they're going to finish the soonest. The hard part is the analysis. This, by the way, is known as Graham's rule, which just goes to show you that if you're born at the right time, you can get your name associated with a really simple idea. That's harder nowadays. So to analyze this, we need to compare our algorithm to appropriate bounds, right? Since we're doing minimization, we're going to compare it to lower bounds. But what should those lower bounds be? How can we relate our, what are some intuitive lower bounds on how long it's going to take to complete the work?
The sum of the PIs divided by the number of machines.
Good. So the average load of a machine is going to be the sum of the PIs divided by the number of machines M. Okay. And so that is going to be less than or equal to the optimum, right? Some machine has to take longer than the average. So that's a nice lower bound, but unfortunately, it's not sufficient. I can give you a problem where the average is really low, but the optimum is really large. And so if I give you, if the optimum can be much larger than the average, then the ratio between my solution and the average is going to be at least that large. And so I'm not going to have a good approximation ratio, right? So can somebody think of a case where the time to complete the jobs is much greater than the average load?
We have one job.
Yeah, right. So if I have one job, then the average load is the processing time of that job divided by M, whereas the optimum is just the processing time of that job. So any algorithm is going to use time equal to the processing time of that job. And that means that the best achievable approximation ratio against this lower bound is going to be that factor M, which is often going to be very large. Okay. So what do we do about that? Well, we've hit 355, so I'm afraid we will have to find out what to do about that on Wednesday. What we're going to need to do is come up with another lower bound that can somehow get us past this problem with the average load lower bound. And you're welcome to think about how to do that, and we will resume this on Wednesday. Any questions?